Hello everyone. In this session we are going to discuss about time and space complexity of algorithm. In last video session we have taken a brief idea about what is time complexity and what is space complexity. We'll go into detail in this session while taking certain example, and later on we'll also discuss about the mathematical notation for expressing the complexity measures of algorithm. So let us start this. If we talk of time complexity, directly if we go to the term, it's related to the running time of algorithm. I am using the term algorithm. When we talk of the term of program, the time taken by a program to complete its execution, that is dependent on the machine on which we are going to execute it. So the basic idea is to have a generalized approach of determining the complexity of a algorithm. Because if we say that particular algorithm will take 10 milliseconds of execution, it may take 5 milliseconds on another machine, because it depends on its architecture. So we are trying to have a generalized approach, or which we can apply in any scenario. It will depend upon the hardware, obviously the final execution time, but before it is actually implemented, we try to have a functional representation of the growth of the complexity of a particular algorithm. For that, we are interested in finding out all the basic operations which are required to be done while executing the program, and that too is derived from the underlying algorithm that we have written for the solution of the given problem. So usually there could be many methods for finding out the time complexity. If we are ready with the algorithm and we have implemented the program, then we can use this experimental measurement, although it has certain drawbacks we will discuss. And after that, in order to have a generalized representation or a functional representation of the time complexity, we can make use of operation count measurement. Okay, so let us move forward. The first method, suppose we design an algorithm and then implement it in a particular programming language. It depends on what language we are using, and again depends on which machine we are running this program. So keeping the machine fixed, keeping the language fixed, if we run that code for different input size, suppose we are executing a sorting algorithm, like to sort, bubble sort program, where the input could be for 10 elements, or it could be for 20 elements, for 30 elements, any number of elements we can give, but obviously according to the number of elements it will take more time. So that time we are drawing as a graph here and trying to estimate that how many seconds or milliseconds are being taken for complete execution of that program for the given size of input. So as we increase the input, this time is also increasing, because if we are using certain looping in the program, that loop will execute for more number of steps. So here our focus is to identify the constant time operation, or the operations which are being repeated depending upon the size of the input. Okay, this is one of the measure of finding the time complexity, but it is not accurate because we are using a fixed architecture for execution of the code. And other problem, in order to find the time complexity, we are dependent on executing the algorithm. First of all, we design algorithm and then we implement in a particular programming language, and then we are able to see how much time it is taking. But we want that without implementing or without depending on particular hardware. We want to know the generalized or functional time complexity, or we want to know the growth rate of that particular algorithm as we increase the input. Okay, so this is the problem with the experimental approach, that first of all that algorithm needs to be implemented, and the results that we are getting are dependent on certain set of input which we have tried. Maybe some of the input which we have not tried will take less time or more time. So trying all the possible inputs is even tough. So that is again a problem with the experimental approach. And last one I already stated that it depends on particular hardware on which we are executing. The same problem with same input size may take different time on different machine. So we cannot say that this experimental approach is a generalized approach for determining the time complexity of algorithm. So what we do is we try to find out the complexity at the design time by observing the code or by observing the sequence of steps that we have written, that what are the steps in that particular code which are not going to be affected by the size of the input, and what are those steps which are being affected by the size of the input. So how many such total operations are there? We express this calculation in the form of a mathematical function, and that mathematical function we call it as a time complexity. So according to the value of n, how it grows, that growth we need to find out. Okay. So this is that approach I was talking about in the previous slide, that there are some instructions in an algorithm or program which takes constant amount of time, and there are some instructions which are being repeated continuously for certain number of times depending upon the input size. If we talk that there are fixed number of lines of code, and according to that if we try to estimate the time, that would not be a correct measure. But still, because in that single line there could be multiple steps or instructions which are being executed or which needs to be executed, that will make a different calculation of time. So those things we need to identify. There are various levels. We can talk of at line level, that line by line how many lines are there, and estimate the time with some assumption, or we have to divide the particular sub steps in a single line of code which are taking certain time, and that time could be calculated. Even if we talk of assembly language programming, a single operation at high level programming language could be considered as a collection of multiple sub operations at assembly language level. So if we at design level, we are simply focusing on the sub operation in the given statement, and that we try to calculate and how it varies with the input. That analysis we do through certain mathematical function. So before going into detail of a particular example how we calculate the steps, let us discuss about this running time, which could be average, best and worst case. See, if we have designed an algorithm, even if we have implemented on some specific architecture, we could have different running time for the same algorithm on the same machine. How? It depends. Suppose you have written a program to find element in a given list of elements, searching algorithm, okay, and you are applying linear search. If the data is already sorted which is available with us, and we want to find the element which is at the first position, in that case, if we talk of the coding of the linear search, you must be remembering that we need to apply a for loop. In a for loop, how we execute the for loop, we start for particular iteration I is equal to 0, and then we go up to the last value, and one by one we compare each and every element. If the data is already sorted and we are going to search the minimum element, in that case the for loop will terminate at the very first iteration. Although it was expected to be completed for all number of times, if our element that we are going to search is either available at the end of the list, or even it is not available in the list, in that case the loop would have been completely executed. But in case because of the certain particular input, we are able to get the result within a single iteration. So that would be the best case for that particular algorithm, where we are able to find the result without completely executing the for loop. So such case is called the best case. What could be the worst case? The element which we are trying to find is not in the list. In that case, the for loop will completely check one by one all the elements and still it will not find the result. So that would be the worst case. Or the element which we are trying to find out is the last element in the given list. And average case could be the middle element is our element of interest that we are trying to find out. So that way any algorithm, depending upon certain input, on which fashion the data is arranged and on which fashion the input is being given from the user, depending on that we can have 3 cases of running time. Even being the algorithm same, even being the machine same, everything is same, but because of the variation in the input, we are having these 3 cases: average, best and worst case. So because of this possibility, even we have 3 types of timing for particular algorithm, like what could be the maximum time taken by that algorithm which we have designed. Best case, like if everything is according to the favored condition, like minimum input is such a way that minimum number of steps are executed from the given set of operations. In that case, we can have best case time complexity, and in between these two will have average case time complexity. So depending upon whenever we write a code, that code may not execute completely depending upon the input. So because of these we have 3 cases of execution. Now how we calculate the number of operations? That is again based on some assumption. Sometimes a single line is taken to be a single operation, but if we go into greater detail, we can focus on individual operation as a primitive operation. The basic operation which according to our own understanding we cannot break further. Although there are possibility of further breaking, but we limit ourselves to the extent that a single statement that we are writing in a C language like I is equal to 0, semicolon, there is only one primitive operation of assignment. So similarly, if we evaluate an expression, there could be certain operations, individual operation in that could be considered as one primitive operation. Calling a method again could be considered as a primitive operation, or returning from the function. Such type of operations in a given algorithm we try to identify and count them, and to make that mathematical function to estimate the growth of time according to the given input. Okay. So I'll take an example of insertion sort to estimate the time. In your previous classes you must have seen the sorting algorithm, where insertion sort is one of the techniques to arrange the elements in increasing order or decreasing order. So if we assume that there are n elements in the array A which we want to sort. So what insertion sort do? Insertion sort is based on placing the given element at appropriate position. What we do, we take first element at the first position, and then we place the second element in such a way that the first 2 elements which are under consideration for the current time are sorted in itself. As we do in case of cards, we arrange the elements. First element is already sorted, second element in such a way that the given 2 elements are placed at appropriate position, and then we take the third element. So using that concept, this algorithm is implemented for I is equal to 2 up to n, because first element is also already assumed to be sorted. So what we do is we place this second element at position of I in the variable key. Okay, so j is equal to I minus 1. Start from the first element 3 and forget about the remaining element. So if we talk of this only element, first element 3, it is assumed to be sorted in itself. Next time when we will start from the second element 1, this particular value we have to place in this array of 2 elements as sub-array, such a way these 2 elements are sorted. For that, what we'll do, we'll move this 3 towards right side and we'll make a space for 1 here, and then we'll place 1 at this position. So this first 2 elements would be sorted out. Similarly, if the 2 elements are sorted, we'll place 4 in the list of 3 elements, such a way that this 4 is sorted. And same process repeated for every element. This is the basic idea of insertion sort. So the same thing we are implementing here, starting from 2, because first element is already assumed to be in the proper position. We'll store this ith index element in the key variable, and we'll reduce this I value from j in the form of j from I to I minus 1. That means if it starts from 2, it will now be 1. So j carries the position from where we need to move the data. So while j is greater than 0, because 1 by 1 we need to shift this data to the right side. So till it is not 0, till that particular time, and till this aj is greater than key, the element that we have stored in the key and the element which is currently at index j, we are going to compare. We have to shift only those elements which are greater than the current element which is stored in the key. So for all such elements, what we do, we move towards, we move all the elements to one position next. So at aj plus 1, we'll place aj. So j is equal to j minus 1. That position, like if we need to move 7, then we'll keep on making space. In order to make the space, we'll move this data 4 towards this side, towards right side, 1 towards right side, 3 towards right side, and that too depends on whether this element is less or greater. For that, we are checking this condition. And finally, whatever space is generated because of this shifting, at that particular position, we are placing the given key, which is the appropriate place. So there is this logic has been explained, but for this example, you need to focus on how many times the particular instruction is being executed. In this example, I am assuming this single line as one operation, and that single line takes certain constant amount of time for execution, and our focus is to determine how many times this instruction is executing. So for this particular loop, which again itself is also having certain sub operations like assignment and then checking condition, increment, that is there, but assume to be a single line of code having certain constant amount of time equal to C1. Okay, so this assignment operation equal to C1, and how many times this kind of process is being repeated because of this for loop. It will repeat from 2 to n and 1 for when it will fail. So total of n times this particular loop is going to execute, and each single step of this loop will take C1 constant time. So it is multiplied by C1. So total we get C1n. Similarly, this assignment operation, if it takes C2 times constant amount of time, which depends on machine, hardware, we are not going into that, but we are assuming is a constant. So, but this constant amount time would be repeated for certain number of times. How many number of times? N minus 1 number of times, because it starts from 2 up to n. So for n minus 1 times, this constant amount which is to be taken by this statement is multiplied by C2. For execution of this statement, j is equal to I minus 1 will also take certain constant amount of time. Let us suppose it's C3, and how many times the statement is executing inside the loop is n minus 1. Similarly, this while loop, which is again nested inside this for loop, for that for this single particular evaluation of this statement which is having while loop for single iteration, the time taken is assumed to be C4, and how many times it depends on this I value, and again inside for each value of I how this j varies. So there would be some complex calculation to find out the number of times it is executing, because for every value of j, depending upon the value of j, this while statement would be evaluated. For that we are using an expression t here to count the number of times this particular statement is executing. suppose it is equal to T2 plus T3, like T2 here represents how many times this while loop execute for I is equal to 2. Okay, for I is equal to 2, how many times this while loop, this particular line written as while loop executes for I is equal to 2. That could be 1, 2, 3 depending upon this condition. Similarly, how many times this while executes with I is equal to 3 and up to I is equal to n. So total sum of these repetition operation is given to be T. Okay, as a summation operation we can represent this T as j is equal to 2 to n. We have to add up all such values T2, T3, Tn for j2 to n. Okay, now if we talk of this particular operation where we are shifting this data aj plus 1 aj, that C5 is a constant amount of time for single time execution, and how many times it is repeating? Overall it was repeating for this particular t times, but we are removing all iterations which are because of this 4i loop, because otherwise it would be repeated calculation for the number of times. So we are reducing this n minus 1 from t, how many times it is executing, because this is a nested loop and we are using this calculation of t to count the number of times this expression is executing. So from t we subtract n minus 1, okay, to avoid the repeated calculation of the operation execution. Similarly, this statement inside the while loop will take t minus n minus 1 time, and C6 is the constant amount of time for single expression. For aj plus 1 is equal to key, let's suppose C7 and n minus 1. Comments do not take any time, that is assumed to be 0. And similarly, these values we can calculate and add up all these to find out the generalized time complexity, where the C1, C2, C3, C4 will vary from machine to machine, that on which machine it will take how much time. Okay, that we can add up to find out the total time complexity, an estimate of the total time complexity in the form of a function. So if we add all these things, we'll get this time taken for n inputs or to arrange the data of n elements by insertion sort would be adding up all those calculations. Okay, so in this calculation there could be 3 cases: best case, average case and worst case. What was the best case? When data is already sorted. If the data is already sorted, the while loop that we have seen in the last slide, this particular while loop, if data is already sorted, this condition will always fail, and these two statements will never execute. So that will reduce the timing of execution. So in that case, we can say that the small ti's, all ti's would be 1, and if it is 1, for ti 1, if we calculate this particular expression, we can find that tn is equal to this c1n, c2n minus 1, c4n minus 1, separating all the constants separate and all n terms together, we'll get this expression. So anyhow, these all are constant. If we consider all these as a single constant, we can write a linear equation. So in that case, if it is the best case, in best case we'll get linear ordering of the execution time. Like it depends, it directly proportional to the size of n if we are executing in the best case. Okay, this calculation we can make use here in order to find the value of j2 to n. This is simple natural number addition formula. As we are starting from 2, so we are subtracting minus 1 here. Now the second case is worst case, when the data is completely reversed or the data is not present. Okay, in that, the data is completely reversed. In that case, we'll have to check for each and every element, and the while loop will completely execute. In that case, the value of ti would be equal to I, because for the loop will completely execute according to the value given by I. every step will execute according to the value of height. It will not be 1. So in that case, we will consider these numbers in the expression, and if we consider these numbers in the expression as a value of t or tn minus 1, the equation that we'll get would be a quadratic equation where the highest order term is n square. That means as we increase the number of input, in case of worst case, the time will increase in the form of a square, like quadratically it will increase. Suppose input is 10. In case of best case, will time complexity in the form of tens of units. But if we are giving input in a worst case scenario and the input size is 10, that total time will be in the power of 10 square, like hundreds of units of time would be taken. So that gives the growth rate of the time complexity in the form of this function. Actually, we analyze the operations which are taking constant amount of time and the operations which are depending on the input. Whether there is any nesting of the for loop or while loop, is there any operation dependent on another operation, that we have to analyze in order to make this overall mathematical function for analyzing the complexity of a given algorithm. So what we concluded is, for a given algorithm, we need to identify the basic primitive operations and how they are repeating. Based on that, we'll define a mathematical function, be it a linear function or quadratic function or any polynomial function. It depends on the steps that we write in the algorithm. And again, if we have determined this function depending upon the input scenario or depending upon the average case, best case or worst case scenario of the input, we can have linear growth or quadratic or polynomial growth depending upon input as well as depending upon the design of the algorithm. So here what we have assumed is some constants. Those constants depends upon the machine on which we are executing this algorithm. Let us move ahead on this direction. Suppose in a algorithm that we have already taken in last video class, 4n plus 6 are the primitive operations to a total number of operations in that algorithm which are calculated, and where n is the size of the input. Depending upon this size, it will vary linearly. So if A and B parameters we consider, as we are not aware of the timing, or we are not aware about the input, that whether it is going to be in worst case, best case or average case, we assume that the A is the time taken by the fastest primitive operation. In any of the machine architecture, this is the fastest machine which will take A time for completing the primitive operation. Okay, fastest primitive operation. And then B is the time taken for the slowest primitive operation. So anyhow, if there are total 4n plus 6 primitive operations, out of which some could be slower, some could be faster, our time will vary between A times 4n plus 6 to B times 4n plus 6, where this 4n plus 6 is the total operations in a given algorithm. So this variation we can express in the form of a mathematical notation, a mathematical function, an estimate about the maximum and minimum time we can provide. So going into more formal, we have certain notations to express the time complexity, that we call it as asymptotic notation. So the first example that we take under the asymptotic notation is big O notation. Big O notation is a mathematical model to predict the growth rate of the given algorithm in the form of a function. So whatever number of primitive operations or steps or lines of code we have calculated in the form of input size, we name that function as fn. Okay, so fn is given the name to that function, and we calculate another function to be the big O of g of n, and that function will give the upper bound on the given primitive operation function, which we call it as Fn. So Fn is the total number of primitive operation whatever we calculated. On that function we find another function as a upper bound. What do we mean by upper bound? That this is the maximum time complexity the given algorithm can take. Okay, it could be loose upper bound or tight upper bound, we'll discuss later on, but that gives a maximum or upper bound on the time requirement of a given algorithm. How we formally define it? There exists a positive constant c and n naught such that for all n greater than equal to n naught, this c times g of n is either equal to fn or greater than fn always. What this graph shows, we are having this variation, like this is value how this fn is changing with the given value of n, and this is the value of c times gn, how it is varying. So in between you can see certain fluctuation, that is acceptable, but after certain point of time, which is n naught, again is some value of n, a positive value of n, after which this fn function is always less and c times gn is always greater. So we are interested in that value of c and that value of n, which we call it as n naught, after which this function becomes always greater or equal to fn. Such type of coverage to the given function fn by gn is said to call as big O notation. Okay, because it gives upper bound. So whenever such questions are given, we need to identify that value of c and n naught. And basic idea is to estimate the maximum time or worst case time of an algorithm by this notation. So if we consider this function n plus 5, let us say it is fn and n square is gn, so we can simply say that it is big O of n square. Anyhow, if we take value of n to be 1, n square is 1 equal. If we take n value 2, it is 2 plus 5 7, it is 2 plus 5 4. So by some method we need to find out that value of c, constant c, which will multiply to n square, and the value of that value of n, after which this n square is always greater than n plus 5. We will see through some example. Suppose the value of fn which is given to us is 8n plus 7 and value of gn is n. To prove this, what we need to find out the value of c, and for what value of n, fn is always less than gn. Okay, for this purpose what I am doing is 8n plus 7, I am assuming that it is less than equal to c times n, where I don't know about c and I don't know about that value of n, after which this c of n, c times n is always going to be greater. So assume that c is 15. This is assumed on the basis of this coefficient 8 plus 7. So c is 15. If it is 15, then 8n plus 7 should be less than equal to 15 times n. And if we solve it, 8n by right and left hand side, if we solve it, 7 less than equal to 7n. But this is only possible when n is equal to 1. This particular condition is possible when n is 1. In that case, we are able to find out the minimum value of n, after which it would be greater. So that value of n is 1. If we take n is equal to 2, then 8 into 2, 16 plus 7, 23, and this 15 times n, that would be 15 times n, that means 45. So that value is always greater. After minimum value 1, after that whatever value we take, that value would always be greater. That was our objective. For such values we are interested, and if those values we are able to find out for two functions, then we can establish this relationship that fn is big O of g of n. Okay. Another example is fn is given to be 2n plus 2 and g of n is n square. can we say that fn is big of g of n, like g of n covers this function fn. In that case, we'll take 2n plus 1 two values and power of n value for some values of n 1 by 1. If we assumed n is equal to 1, fn would be 2 into 1 plus 2, 4, and gn would be 1 square, that is 1. So in this case, fn is greater than gn, which is not true. That means this value of n is not valid. We need to increase further. So we take value of n2. In this case, fn is 6. If we calculate 2n plus 2 and gn 2 square 4, again it is fn is greater, but what we want, fn should be less. So in this case, again we take n is equal to 3. Fn, if we calculate here, that would be 8, and gn square of 3 would be 9. In this case, the very first time for n is equal to 3, we get fn less than gn. But after that, if we increase the value of n, it will always be satisfying this condition. So the value in which we were interested to know is n naught is greater than 2 or equal to 3 onwards. So for all n greater than 2, this g of n is greater than fn with c is equal to 1. So c value is 1 and n should be greater than 2. Because these constants exist for these two functions, in that case we can say that fn is big of g of n. So I hope this example is clear. Okay. So that was big O notation. The other notation that we use is omega notation. Omega notation is just opposite to the big O notation, where we try to find out the lower bound, the minimum time or best case time. Okay. This notation says that if we have two function fn and gn, we can say that fn is omega of g of n only when we are able to find some constant c and n naught. Okay. For some constant n naught, where if we use c times g of n, it is always less than fn. In previous case it was greater, now it is less than equal to fn. If there exists certain constant c and n naught, for which c times g of n is always less than f of n, in that case we say that fn is big omega of g of n. So same way, fn is now above c of g of n. So below this, we cannot go below this. This is the minimum time, minimum complexity that we can achieve, and that too possible if there exist certain constants. So that way it gives a lower bound to this fn. Okay, omega notation. If we consider an example on this, similarly we'll again calculate the constants. If we are given this example that n square plus 3n log n is big omega of n square. So what we have to prove actually, that c times n square is always less than this function. So for that we need to find out c and n naught. So n square plus 3n plus log n, let us suppose that it is greater than equal to cn square, and in that case, if we further calculate for n equal to greater than equal to 1, it would be surely greater, because if we are putting n equal to 1 square plus something, something positive is definitely going to be greater than n square. So it is proved. So on the basis of this, with n value greater than equal to 1 and c value 1, we say that this particular function is omega of n square. Okay. And the last notation that we use is for average case, or theta notation. That means the given function or number of primitive operation that we calculate and represent it as through a function fn, that should lie between gn, and that gn on the upper side is multiplied by a constant c2, and on the lower side it is multiplied by c1. That means in this case we need to find out three constants. One is c1, another is c2, and third one the value of n, which after which this c1 times g of n is above fn and c2 times g of n is below fn. That kind of relation if exists between two functions, in that case we can say that fn is theta of g of n. Okay, so this kind of like we can say equal to average is just equivalent to equal or just about to equal. The time complexity which represents the middle case, not being best, not being worst, it is equivalent to the average case. For that we use this notation. Okay. So in brief we can say these are the representation that we use, that in all these three cases n naught implies that after this value of n, we do not care about the further values of n. According to the particular case, it will definitely satisfy all the given conditions. In case of theta, for value of n naught, there will be some function gn, to which if you multiply c1 it will be less, and if you multiply c2 it will be more than f of n. Okay, that kind of relation will satisfy. For n naught in case of big O notation, fn is always less than c times c of n, and for n naught in case of omega notation, fn is always greater than c times g of n. This particular case gives the best case time complexity, this particular case worst case time complexity, and this particular case gives average case time complexity. Okay, so there is some short notation that we usually use, and we can also have look on these in future. Like big O is just equivalent to writing less than equal to condition. Like this should be in the condition that fn is always less than equal to. In this case, fn is greater than equal to. In this case, almost equal to, we can say. And there is a notation called small o. The only difference is this equal to sign is not there, and small omega without equal to, like that condition, strictly it should be less or greater, that we use. So that was brief about the asymptotic notations that we have gone through examples. Now there are some rules while defining the big O notation. That big O notation actually represents the growth of function, and that growth also in case of very large size input. If the input, that means the value of n is in billions or millions, in that case comparatively we can ignore these small constant values 4n plus 5, that we can write 4n. Even this coefficient for very large value of n is ignorable. So all such values while writing the big O notations are ignored comparatively, because we state the growth for very large value of n. Okay, similarly 0.5 n log n could be written as n log n, of log of n square could be by logarithmic mathematical function could be written as 2 log n, and further by ignoring this constant we can write to log n. So these rules somewhere are applied on big O notations. Now if we talk of space complexity, the calculation is almost similar, but the focus is on different aspect. In this case, we are interested in finding out the space requirement, memory requirement of the algorithm. So it depends on many parameters. The instruction space, like how many instructions or lines of code we are writing, and that takes certain memory. Data space, what amount of data we are going as an input to the function, as an input to the algorithm, and what is the size of single data item taken by the particular machine, that depends on that as well. And sometimes on environment stack space. Environment stack space is depending upon certain function calls sometimes. Like if we talk of recursion, it makes use of recursion stack. That is a temporary memory area taken to solve the particular problem. So that also adds to the space requirement. So the type of calculation that we did in case of time complexity, we can also do in case of space complexity while counting how many variables we are using, and what is the size of individual variable in a particular language, that we can calculate. What are the variables which are dependent on the input, and what are the variables which are not dependent on the input. So in that sense we can do this kind of space complexity analysis as well, and the same notations we can also use. Okay, so we'll take some small examples to see how space complexity we can calculate. For example, if we have this small program where we are defining 4 variables A, B, C and Z. In A we are giving the input, so this input will take certain memory, and this result is also stored somewhere and it will use certain space. These lines of code as well will take certain memory while storing the data. So depending upon the compiler or the operating system, every variable takes certain fixed amount of memory. There is an assumption that character takes 1 byte, short int takes 2 bytes, integer takes 4 bytes, float takes 4 bytes. With that calculation, if we calculate the memory requirement for this, rough estimate which is coming to be here for 4 variables is 16 bytes. As a 16 bytes. That could be different with some other assumptions, but anyhow, whatever you will calculate for this particular program would be a constant number. That is not dependent on any external input. Everything is inside this code. There is no external input, and it is a constant space program. That means it is not varying. Whenever you execute, wherever you execute, it will take 16 units of space depending on any particular machine. So such type of programs are called constant space program. Its complexity is constant. We'll take another example. This particular program makes use of for loop, and that for loop is executed depending upon the number of inputs that are given to this function. So in this case, this value of n is given by the user, and that user may give 1, 2, 3 billion hundreds of number to store in this array. So if single array element takes a certain fixed number of bytes, let's say 4 bytes, so n will take 4n bytes to store. Similarly, this x variable will take certain amount of memory, let's say 4 bytes for this, I will take memory 4 bytes for this, and 4 bytes for n. Okay, some calculation and return statement finally. So that way we taken calculation for the insertion sort. We will focus here on the memory part, and 4 into n for n elements of 4 bytes each. And then we calculate amount of memory for constant variables that we have used, which are not dependent on the input. So there are 3 variables x, n and I. So finally we have a mathematical function depending upon the input 4n plus 12. So this 4n plus 12, that we will consider as a space complexity function, which we can call it as a fn. So if we calculate big O of this, that could be n. If we ignore these constants and coefficients, we can simply write big O of n. That means its space complexity is linear order. The space is increasing linearly whenever we increase the input size. Okay, that way we can have another complex examples as well, and we can represent the space complexity as well in quadratic or polynomial space complexity. Okay, so in this session we discussed about time and space complexity, their importance, and how we calculate that, how we use asymptotic notations to represent the time and space complexity. So in the next class we'll be discussing in detail about time-space trade-off and abstract data types. I hope you enjoyed this video. If any query you can give in comments. Till then, thank you.